Welcome to Dr. Boxy Teaches Probability Theory and Statistics. In this course, I will cover the material usually taught on these topics in a first year of an undergraduate degree of physics or mathematics, and as such, the only real prerequisite, the only knowledge that I will assume you have is a high school level of mathematics. The material will cover on the probability theory side. We will start by simply defining the concept of probability. What does that word actually mean? And then we will look at random variables, both continuous and discrete. We will look at the most often used distributions, and we will end the probability theory part of the course with a discussion of the central limit theorem and some of its applications. Then we will go to statistics, and in the statistics part we will look at ways to describe and study properties of populations. We will study the different techniques to apply probability theory to study those things, to infer from data about populations more general results, and we will look at a number of very important topics in statistics with a focus on hypothesis testing on the one hand and confidence intervals on the other. The course will be mostly based on the book Mathematical Statistics and Data Analysis by John Rice, and throughout the course I encourage you to send me questions, leave comments below. I'm very happy to interact with you. Let me know if anything is unclear. All feedback is very, very welcome. So welcome to this course. Let us get started. Why study probability theory and statistics in the first place? Well, among other reasons, one very good reason is that it is one of the most widely applied, used branch of mathematics. Its applications range from understanding the odds of winning in a game of chance to understanding quantum mechanics. If we want to understand many of the algorithms behind artificial intelligence, we want to be able to predict the weather, we want to understand how our genes make us as humans, well, all of these are applications of this theory. And the central concept in probability theory and statistics is the concept of probability. So let's start by trying to understand what we mean by that word. Before we even go to a formal definition of the word probability, let's try to intuitively understand what we will want to mean by that word. And so, as an example, as a simple example, let us look at throwing a die, and we know that the possible outcomes of that throw are the numbers 1 to 6. Now, the set of all possible outcomes of such an experiment will be known as the sample space. I use the word experiment here, but the word experiment in this context is meant in a very broad sense. Basically, what it means is you do something that has some aspect of randomness in it, and all the possible outcomes, we collect them in a set known as the sample space. And an experiment is basically just saying we do something. So an experiment can be throwing a die, but it may also be I throw a coin up twice and I keep track of whether I get heads or tails. And in that case, the sample space can be either 2 heads in a row, or a head and then tails, or tails and then heads, or 2 tails in a row. Another possible experiment can be I play some game of chance and I keep on playing it until I win one time. The sample space can be how many times do I need to play the game before I actually win it? Well, it can be that I win after one game, and in that case the outcome of that experiment is 1. It may be that I have to play it 7 times before winning, and in that case the outcome, the element of the sample space that we found in that case, was 7. So in principle, the sample space in this example would be all the positive integers. Another possible experiment can be we throw a dart onto a dartboard, and let's say that the dartboard has a radius of 1, and we draw a coordinate system on that dartboard with its origin in the bullseye at the center, and we keep track of where the dart lands. Well, in that case, the sample space is any point within the dartboard, assuming that we actually hit the dartboard, and in that case the sample space are all the couples xy that are within a circle of radius 1. If we were to take into account the fact that you missed the dartboard, we can actually add just one element to that sample space, just call it the element out, and then the sample space would be all the couples xy that are within a circle of radius 1, with one additional element being the element known as out. So the sample space is every possible outcome of an experiment. Now we will also look at a concept known as an event. And it sounds a bit like a circular definition, but an event is basically anything where we can ask what is its probability. So going back to the sample space of a die, throwing a die, one possible event can be I throw a 5, and even without defining the concept of probability, we have an intuitive understanding of what the probability of throwing a 5 would be. If we're looking at a fair die, the probability of throwing a 5, which will be denoted by P of F, P for probability and F is the event of throwing a 5, well, the probability of that event is 1 out of 6, so 1/6. Another possible event can be throwing a 1 or a 4. I call that event G, and the probability of that G, again, intuitively, we understand it to be 2/6, which is 1/3. Another possible event can be throwing an even number, so that would be a 2, a 4, or a 6, and the probability of that event would be 3/6, which is 1/2. So an event, in this sense, is simply any subset of the sample space. Once we have the concept of an event, we can use it to build new events using it. And so one possibility is if we start with some event A, we define a new event, A superscript C, we read it as the complement of A, and that event is the event of A not happening. That means that it is the event of all the elements of omega of the sample space except for those that are in A. So for instance, if we think again of omega as being the sample space of throwing a die and G is the event of throwing a 1 or a 4, the complement of G is not throwing a 1 or a 4. In other words, it's throwing any of the other possibilities, which is a 2, a 3, a 5, or a 6. So that is the complement of an event. Another way to produce an event based on some previous given events is using the union of two events. So A union B, it's read as A or B, is the event that encompasses all the possible outcomes that are included in at least one of the two A or B. So if this is the event A and this here is the event B, A or B includes all of it. So for instance, if G and H are the events as I define them on the right of the slide, then G or H is all those elements, all those outcomes that are included in at least one of the two. And that means in this case it's a 1, a 2, a 4, or a 6. And notice also that whether we write A or B, or we write B or A, the resulting event is the same one. So that is the union of two events. A third way of creating an event based on previous ones is using the intersection. A intersected with B, and it's read as A and B, is the event that has as its elements only those elements that are included in both A and B. So it's only this part here. So again, for G and H as I took them before, G and H is only 4 because it is the only element of the sample space that is included in both G and H. And just like before, whether we look at A and B or at B and A, the resulting event is the same one, namely the intersection of those two events. We also introduced the notion of disjoint events, and they are known as disjoint when they don't have anything in common, meaning that the intersection of those two events is the empty set, and the empty set is denoted by this symbol here. So two events are said to be disjoint if they do not have anything in common. Let us look at some intuitive properties of probabilities of events. The first one is that whatever event A is, it either happens or it doesn't. So the probability of A happening plus the probability of A not happening is 100%. is 1. Secondly, whatever event A and B are, if A is included in B, if A is a subset of B, then the probability of A happening is less than or equal to that of B. To understand that with an example, consider one of the events, F, being I throw a 5 with a die, and K is throwing a 1, a 3, a 5, or a 6. Clearly, F is a subset of K. Throwing a 5 is one of the possibilities, including in throwing a 1, a 3, a 5, or a 6, and therefore the probability of throwing a 5 is included and has to be therefore smaller than the probability of throwing a 1, a 3, a 5, or a 6. Finally, another property is that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And to understand this, let us look at the graphical representation of this. So whatever A and B are, A or B, we said these are, let's say, A and B. So A or B is all of this. Well, if we look at A alone, we have this. If we look at B alone, we have that here. And notice that what I'm doing here when I'm adding them up is adding the probability of being in either one of those two circles. But I double counted, I overcounted something, namely those elements that are included here, that are included in the intersection, included in both of them, I counted them twice. One when I calculated the probability of A, and a second time when I calculated the probability of B. And so to correct for this overcounting, we need to subtract the probability of that intersection, so the probability of A and B. Let us look at this last property at work using a numerical example. So if we throw a fair die, I want to know what the probability is of getting either an even number or a multiple of 3. So event A would be an even number, meaning it is either throwing a 2, a 4, or a 6, while event B, throwing a multiple of 3, would be throwing a 3 or a 6. Notice that A or B is the event that includes all the elements that are in at least one of the two, meaning it is 2, 3, 4, and 6, while the event A and B are those elements that are included in both of them, and only those that are included in both of them, which is only the 6 here. Now, what is the probability of A or B? So that is what we're actually looking for. It's the probability of throwing an even number or a multiple of 3. Well, as we can see, there are 4 elements in there, 2, 3, 4, and 6. So the probability of that is 4 out of 6 possible outcomes. What is the probability of A? Well, A is throwing an even number. There's 3 out of the 6 here. And the probability of B is 2 out of 6, a 3 or 6, so that's 2 out of 6. In other words, those two taken together, the probability of A plus the probability of B is 5 out of 6, which is not the same as the probability of A or B. We get 1/6 too many. Why does that happen? Well, simply because we calculated the probability of throwing the 6, the number 6, twice, once in P of A and once in P of B. We have overcounted exactly that outcome that is included in both of them. So if we were to subtract the probability of A and B, which is 1 out of 6, if we were to subtract this from the 5 out of 6, we would indeed get 4 out of 6, which is the probability of A or B. Until now, I haven't actually defined the concept of probability. I just used it in a hand-wavy, intuitive manner. Because we're doing this in a mathematical way, we want to make sure that we understand what the word actually means, so we need to define it mathematically. And we will use the following definition. We start with some sample set omega, which is the set of all possible outcomes, and we will define the word probability measure will mean a function which takes as inputs subset of this omega. In other words, it takes in events and it outputs real numbers. If we have a function that takes as its input events and gives as an output a real number, we will call that function a probability measure if it obeys the following three conditions. The first one is the probability of omega itself, of the whole sample space, is 1. That is intuitively saying that the probability that one of those outcomes will happen is certain, so it's 1. Secondly, that the probability of any event, whatever event A is, the probability of an event can never be negative, it's always positive or 0. And finally, that if we take two events, A1 and A2, and they are disjoint, meaning they have nothing in common, then the probability of A1 or A2 will be the probability of A1 plus the probability of A2. And more generally, if we take not two disjoint events, but many disjoint events, A1, A2, A3, and so forth, and they are all mutually disjoint, meaning that each pair that you would choose is disjoint, then the probability of the union of all of them is simply the sum of the individual probabilities. So any function that takes as its input subsets of omega, in other words, events, and it outputs a real number with those three conditions will be known as a probability measure, and that is how we define the word probability of some event. Now, I do want to mention that this is still relatively hand-wavy in the sense that I did not define what a sample space is, at least not from a mathematical point of view. I did not use a formal definition using set theory to define what is and is not allowed to be a sample space, nor did I define what event is exactly. I'm claiming here an event is a subset of omega, but can omega be any set imaginable? And can any subset of that omega be an event? Well, to define that properly, we need to go beyond what we will discuss in this course. And this is something that is usually done in a later course on either probability theory or Lebesgue integration, because both of them use something known, a branch of mathematics known as measure theory. And in measure theory, you define those concepts in a very formal way that allows you to use it in a mathematically rigorous way. Now, in an introductory course on probability theory, usually the measure theory approach is not used, and I will not use it in this course, but I refer you to a future course I will make on measure theory in which we will come back to this definition but do it in a more formal way. This will be the definition of a probability measure in this course, and this is what we will use throughout the rest of this course. A couple of slides ago, we looked at some properties of probabilities of events, but we reasoned them intuitively. But now that we have a definition of the concept of a probability measure, we can actually go and prove them such that we get a theorem. So these are the three parts of the theorem, and at the top right of the slide, I wrote the characteristic defining properties of probability measures, and we will use them. That's all we have that we can use to prove the theorem. So let's go through each of those three parts of the theorem. Firstly, we can write omega, the whole sample space, as the union of A and its complement. This is simply because the complement of C is defined as anything that is in omega but not in A. And because of this same defining property of the complement of A, we know that A and its complement are disjoint. In other words, their intersection is the empty set. Now, using the first property of probability measures, we know that the probability of omega is 1. Now, the probability of omega can be written as the probability of A and the complement of A. And because they are disjoint, using the third property of probability measures, this can be written as P of A plus P of AC. And this proves part A of the theorem. For part B, Now we are given the fact that A is a subset of B. So how can we prove the fact that PA is less than or equal to PB? Well, we can write B in the following way. B can be written as A union everything that is in B but not in A, and that is written as the set theoretical difference of B and A, so that's B minus A. So this is a notation for everything that is in B but not included in A. And for the same reason, that means that these two are disjoint. A intersected with B minus A is by definition the empty set. And so we can write the probability of B as the probability of A union B minus A. And because they are disjoint, we can write them using the third property of probability measures as P of A plus P of B minus A. And now we can say that this is larger than or equal to P of A alone, where I simply got rid of the P of B minus A. And the reason I can say that is because of property number 2 of probability measures. We know that P of B minus A is a non-negative number. In other words, this inequality must hold, and this proves part B of the theorem. For part C of the theorem, we will use different ways of writing those events in that expression. So first of all, I want to rewrite the event A or B somehow. Well, A or B, remember, if we take A and B to be those two events represented graphically, A or B is simply all of it. Well, if this is A and this is B once again, I can write A or B as, first of all, A minus B. So that is this part. It's that part of A that is not included in B. Union that part of B which is not included in A. So it's this part here. Union the intersection, which is the only thing that we're missing here. So that's A intersected with B. And notice that all of those are disjoint. That means, according to the third part of the theorem, of the defining properties of a probability measure, that P of A or B is P of A minus B plus P of B minus A plus P of A and B. So that is one way to rewrite the event A or B and its probability. Now let us look at P of A and P of B separately. Well, the event A can be written as A minus B union the intersection of A and B. Notice again, A minus B is everything that is in A but not in B, and the only part of A that we're missing is the intersection, and those are disjoint again, meaning that P of A can be written as P of A minus B plus P of A intersected with B. And in a similar fashion, we can write B as B minus A union the intersection, and therefore P of B is P of B minus A plus P of A and B. And now we can add these together. On the left hand side, P of A and P of B, so I get P of A plus P of B. And on the right hand side, I get P of A minus B plus P of B minus A plus P of A and B plus, once again, P of A and B. And notice that on the right hand side, the three first terms are exactly the ones that we have here. In other words, this is equal to P of A or B plus P of A and B. And that is what we wanted to prove. So this proves all three parts of this theorem. I'll put a beautiful QED here. And this is how to prove all three properties of probability measures using their defining characteristics, which I wrote at the top right. For the rest of today's lesson and the whole next lesson, I will only consider finite sample spaces. And from the third lesson onwards, we will go back to a potentially infinite sample space, but I will remind you of this fact when we're there. So we're looking at a finite sample space, and I will denote the probability of each of those elements, so the probability of element omega sub I as pi. Now, if we take some event A, the probability of this A is the sum of the probabilities of each of the elements that constitute it. The reason for that is that A can be written as the union of each of its elements, and that union is a union of disjoint sets. And so according to the third property of probability measures, it is simply the sum of those individual omega probabilities of the individual omega i's. How can we use this fact? Well, if we think of the situation in which we throw a coin twice and we keep track of whether we got heads or tails, we have a finite sample space. There's only 4 possible outcomes, and each of them has a probability of 1/4. If we then look at the event of throwing at least 1 times heads, there are actually 3 elements there: heads and heads, heads and tails heads. And so the probability of A is the sum of those 3 possible outcomes that obey the condition that there is at least 1 heads in them. So it's 3 times 1/4, in other words, 3/4. And what I want to do now is to use this intuition, this fact, to see how to define, or rather rewrite, the definition of the probability in such a special case as this. So we are looking at a finite sample space having capital N elements, but we're looking at a special case of that, namely the case in which each of the possible outcomes has the same probability. So the probability of each of them is 1 over capital N. The reason for that is because their sum has to be, by definition, 1. In that case, let's say that A is some event and A contains little n elements of the total number of elements in omega. What is the probability of A? Well, it is the sum of all the elements in A, but there are little n of them, and so out of the total possible outcomes, which are capital N, there are little n of them that actually obey A. In other words, the probability of A is little n divided by capital N, and this corresponds to a fraction in which the numerator is the number of ways in which A can occur, and the denominator is the total number of possible outcomes. Now we can consider this to be a definition, if you want, or rather a way to calculate the probability of A, but I do want to warn you, this only works when we're dealing with finite sample spaces where each of the outcomes is equally likely. And let's see why that is so. We look again at the case of throwing a coin twice, but instead of looking at the sample space like we did on the previous slide, so on the previous slide we had this sample space where we keep track of each of the outcomes. Let's say that this time we do the same experiment in the sense of throwing the coin twice, but this time we only keep track of the number of heads we got in the throws. In that case, the sample space becomes not the one we have above, but simply the number of times that heads occurs, namely either 0 times, 1 time, or 2 times. If I then look at the event A being at least 1 time heads, if we blindly apply the formula I wrote on the previous slide, namely the probability of A being the total number of outcomes in the denominator and the number of outcomes that obey A in the numerator, then we get in the denominator there are 3 possible outcomes in this sample space, 0, 1, and 2. In other words, I have a 3 in the denominator, and 2 of them, this one and that one, obey A, and so we would get 2/3. But we saw on the previous slide that the probability of at least one heads is not 2/3. The correct probability is 3/4. This simply shows that using this formula as the definition of calculating a probability does not work if the elements in the sample space are not all equally likely. And in this case, in this sample space, they are not equally likely. The probability of getting one heads is double that of getting either 0 or 2. And so just keep that in the back of your mind. It's okay to use the formula I showed on the previous slide as long as you only apply it for finite sample spaces where each of the outcomes is equally likely. As a final point for today's lesson, I want to discuss something known as Simpson's paradox, and I'll do that using an example. So here is a game in which we have both a dark and a light box, each of them containing some number of green and red balls. The game is the following one. You need to pick one of the two boxes, and from the box you've chosen, you pick one ball at random, and you win the game if the ball you picked is a red one. So what is the probability of winning if you choose to play with the dark box? Well, the answer is the probability of winning is 5 out of 11. There are 5 red balls out of a total of 11 balls in the dark box. What is the probability to win the game if you pick the light box? The answer is 3 out of 7. So in this game, you're better off playing with the dark box. Let us now look at a second game. The rules are the same. The number of red and green balls in the boxes is different. What is the probability of winning the game using the dark box now in the second game? Well, the answer is now 6 out of 9. While the probability of winning the game if you pick the light box would be 9 out of 14. So once again, you're better off choosing the dark box. Now, for the third and final game, what we do is we again consider a dark and a light box, but this time the dark box contains the balls from both dark boxes of the two previous games, and the light box in this third game contains all the balls from the light boxes of game 1 and 2. Which box should you choose this time? Well, intuitively you may say, well, the dark box was better in game 1 and in game 2, so obviously if we just throw them all together, it is the dark box that will be the better one. Well, your intuition may say that, but let's actually look at the numbers. The probability of winning this third game with the dark box is 11 out of 20, while the probability to win the game with the light box is 12 out of 21. So you're better off playing in this third game with the light box. Now, notice where the numbers actually came from to understand what happened here. If you actually look at the numbers, the numerator in the fraction that tells you the probability of winning if you have the dark box, the 11 here, where does this 11 come from? Well, the 11 is the sum of the 5 from the first game and the 6 from the second game. So the number of red balls in the dark boxes for game 1 and game 2. Adding those two up gives me 11. Where does the 20 in the denominator come from in the probability to win if you play with the dark box? Well, this 20 is the sum of the denominators of the two previous games, namely 11 and 9. So intuitively you may say that the dark box would be the better one, but what you do is to actually calculate the probability in this third game is add the numerators and denominators separately, and that is simply not how you add fractions to each other. And so that means what Simpson's paradox actually says is that some pattern that may be true on a individual level, when aggregated, can not be there anymore or can even potentially be reversed. And there is a very interesting example of this that actually occurred. There was a study of whether there was gender bias discrimination in admission rates at Berkeley Graduate School in the 1970s. And aggregated over the whole university, it turned out that the admission rate for men was higher than for women, was significantly higher. So the probability of getting admitted to graduate school if you applied being male was higher than if you applied as a woman. Now, the natural question is then, okay, but if there is discrimination, which of the departments or faculties is responsible for this discrimination? Who does the discrimination? And so what they did is they went and looked at each of the departments, each of the faculties individually, and it turned out that at none of those faculties or departments, there was significant discrimination one way or the other. How can it be that if there is no discrimination at each department individually, that there seems to be discrimination on the aggregate, on the total number university-wide? Well, the answer is, for each individual department, the probability of getting admitted if you applied there, whether you were a man or a woman, did not significantly impact your probability of getting admitted. It just turned out that women were applying more often to departments that had lower admission rates. And so as a consequence, when taken over the whole university, it looked like there was gender-based discrimination in those admission rates. So this is just a real-life example of Simpson's paradox. This was everything for today's lesson. In the next lesson, I want to discuss, first of all, something known as the multiplication principle, and then we will look at ways of counting in how many ways something can be done. So there's a branch of mathematics known as combinatorics, which those things are studied, and we will look at concepts known as permutations and combinations. I will see you in the next lesson.